All right, so our next topic is in section 2.3, and we're going to discuss interpretations of the derivative. Now, before I start going into interpretations of the derivative, I do want to make a quick comment about notation. There's a lot of different ways that you can write the derivative of a function. So suppose my function is y equals f of x. One way that you've seen it is we can write it as f prime of x. Sometimes I'm really lazy and I just write y prime. Another way to write it is you're taking the derivative of y with respect to x. Or you could say it's the derivative with respect to x of your function y. I mean, there's so many different ways that we can express the derivative of a function. And I just want you to be aware that they're all equivalent ways and just to be keen on that notation. Okay? So what we want to do in this section is talk about the interpretations of the derivative. In other words, what do they mean in the quote-unquote real world? Well, I think the most common example to begin with is as follows. Suppose I have s of t. And I'm going to call that my position function. Okay? And suppose t represents our time, and s represents essentially the distance. And we can just use meters if we would like to, and time being seconds. Okay? So, what we're essentially saying is s of t is the position of an object at time t. Okay? So, what does s prime of t mean? Remember, whenever you're doing these interpretations, you really want to hone in on units. Okay? The derivative of a function is the slope of the function at that point. Okay? The slope of the tangent line at that point. So, slope is change in y values over change in x values. Well, notice that my function values are my distance, so it's the change in distance over the change in time. And I claim we actually have a real world term to that. That's called our velocity or our speed. So, one thing that we're seeing is that if we have a function s of t, and that's our position function, the derivative is precisely the velocity. Now we can even take this one step further. What if I asked you what's the derivative of our velocity function? Well, let's talk about units. Isn't that the change in velocity or the change in speed over the change in time? And I claim that's precisely what we mean, acceleration. When it's hard to talk and write at the same time. That's precisely what we mean when we talk about acceleration. So if I want to talk about my derivative of my velocity function, in real world terms, that means that we're talking about our acceleration. Now, a little foreshadow here. If I'm taking the derivative of my velocity function, that means I'm taking my derivative of the position function. In other words, I'm taking his second derivative. Okay? So, that's one real world way that I claim that we look at our derivatives quite often. Now, let's just take a few more examples here. And how about this? Let's say, suppose the population we'll call that capital P, and that's going to be expressed in billions, is a function of the year t. In other words, P is a function of t, I tend to just write that as p of t. Okay? So, let's explain the meaning of p of 1990 equals 5.295. Okay? Well, here we're just describing what a function means in words. Start inside at your independent variable. Notice this is the year. So this says, in the year 1990, well, what is this? That's my p-value. The population is 5.295 billion. Okay? Now, let us explain in words the meaning of this. Now let's explain the meaning of p prime of 1990 equals 0.086. Okay? Remember, now we're talking about a rate of change. When we're talking about a rate of change, essentially what we're doing is we're just interpreting the slope. Okay? So, what does it mean when you say that the slope is some value? It means at that point, for each additional x value, your function value is either increasing or decreasing by some amount. Okay? How do we know increasing or decreasing? We know that by the sign of the slope, positive or negative. So, what this says is, starting at 1990, in 1990, for each additional year, well, what's happening to the population? The population, I claim, is increasing because my slope is positive by 0.086 billion people. Okay? In other words, in 1990, as time goes on, it's increasing by 0.086 billion people per year. And in case you really care, that computation comes to about 164 people per second. It's pretty crazy. All right, let's do a couple more here. Let's say that here G of V represents the fuel efficiency of a car moving V miles per hour, and my function G of V is in miles per gallon. Okay? So, let's explain the meaning of G of 55 equals 27. Okay, this is just our function straight up. What this is saying is, hey, when V is 55, in other words, at 55 miles per hour, well, this is our fuel efficiency. The car gets 27 miles per gallon. Okay? Now, let's explain in words this. Suppose we have G prime of 55 equals negative 0.54. Okay? Now again, we're interpreting our slope. So, what is this saying? Well, this is saying at 55 miles an hour, as we increase our speed, for every additional increase in speed by 1 miles per hour, what's happening to our fuel efficiency? What a bummer. It's decreasing because this is negative by 0.54 miles per gallon. So we could say something to the effect of at 55 miles per hour, for each additional increase in speed by 1 miles per hour, the fuel efficiency decreases by 0.54 miles per gallon. Notice I don't write the negative because I've already taken into account the decrease. All right, one more just to be sure that we have sufficient examples. What if I say that the cost of extracting T tons of ore, say from a copper mine, is F of T dollars. Okay, well, what does F of 2,000 equals 30,000 mean? Well, I claim that it means the cost to extract 2,000 tons of ore is $30,000. And what does it mean that F prime of 2,000 equals 10? Well, what we could say is as follows. Remember, this still stands for the tons of ore. We could say that at a production level, of 2,000 tons, each additional ton extracted costs $10. All right, now along the lines of interpreting our derivative, we're just going to go very loosely into an idea in this section called linear approximation. Okay, so I'm going to draw a function, just a nice little generic function. We'll call this f of x, imagine that. I'll call this the point A, and I think you'll grant me that's the ordered pair A, f of A. Okay? Now, I can estimate that my tangent line looks approximately like this. Okay? Now, the thing that's important to keep in mind here is that the tangent line is a really good approximation to the function for points nearby. Okay, so if I wanted to somehow approximate my function over here, and I had the information of my function value at A, I could use the equation of this tangent line in order to approximate my function value. Now, that would be true for this point because he's pretty darn near A. But I claim for up here, that's not going to be worth very much at all, because if I continue this line, okay, it's not a good estimation at all. And then you take a point over here and continue this line, boy, it's nowhere near that. So, sometimes it can be difficult to actually find function values at a point, but if we have information about a function value at the point and information about the derivative, well, we can use that to approximate values nearby. Now let's talk about this, okay? What we're going to be doing essentially is finding the equation of the tangent line at x equals a. Well, we know in order to find the equation of a line, we need a point and a slope. I have my point, a, f of a. And by definition, the slope of the tangent line at a is f prime of a. So what I'm going to do is find the equation of this line using my point slope formula. I have y minus my y value equals m, which is the derivative, times x minus my x value. So, scooting over the f of a, can't we say that y is f of a plus f prime of a times x minus a? That gives me the equation of my tangent line. So if I want to approximate a point nearby and talk about the linearization near A, so I'll say that the linearization of f at the point A is, I'll call that L of x, is approximately equal to f of a plus f prime of a times that x value minus a. Okay, so what I'm going to do, and I will grant you, you can do a lot of these sorts of things in your head, is I'm going to actually take an example and tie it in with our interpretations. Okay, and then we'll find the linearization at a couple of points. All right, so this example that I'm looking at says for some painkillers, the size of the dose D, so D is the dose, given depends upon the weight of the patient, W. That makes a lot of sense. In other words, we have D of W. Okay? So what I want us to do, just to kind of tie all this together, is first interpret D of 140 equals 120. And let's just suppose our weight's in pounds and my dose is in milligrams. Okay, so what does this mean? What this means is that for a patient weighing, or for a person who weighs 140 pounds, the dosage is 120 milligrams. All right. Now, one hopes someone doesn't use linear approximation much to do dosages, but let's keep going. What does it mean now for D prime of 140 to be equal to 3? Let's interpret this in terms of the painkiller. Well, what this means is as follows. At 140 pounds, for each additional pound, the dosage will increase because my slope is positive, my derivative is positive, by 3 milligrams. Okay? And finally, let's apply this linearization. Let's use the linearization and this information that we have as follows to estimate two things. Let's estimate D of 145, and then let's estimate D of 137. Now, I'll grant you, you can do this in your head, but humor me and let's use our linearization formula. Okay? Notice this is my X value here. So plugging it into my linearization formula, look, we've got the information at 140, so I'm going to claim that that's approximately equal to D at 140 plus D prime of 140 times 145 minus 140. So, using the values given, we can say this is 120 plus 3 times 5. In other words, the dosage is approximately 135 milligrams. All right, now let's do this one. Well, again, we've got the information for 140, and yes, we have an estimation for 145, but we want to go as close as we can to our value. So we have that's approximately d of 140 plus d prime of 140 times 137 minus 140. So here we have 120. My derivative is 3, and 137 minus 140 is negative 3. So this is equal to 111 milligrams. All right, thank you. I hope this was helpful.